Right now, thousands of data streams are passing straight through you. We live inside a chaotic, invisible web of overlapping electromagnetic waves, carrying everything from financial trades to video calls. We generate exabytes of data every month, but the physical medium carrying it, the electromagnetic spectrum, is strictly finite. It cannot be manufactured, stretched, or expanded. Early telecommunications relied on rigid analog broadcasts. A single continuous electrical wave carried a single stream of information, requiring massive towers to push high-power signals over long distances to overcome physical obstacles. In 1948, Claude Shannon proved that the capacity of any communication channel has a strict mathematical limit. The Shannon-Hartley Theorem states that channel capacity, C, is entirely bound by just two variables, the available bandwidth, B, and the signal-to-noise ratio. Signal-to-noise ratio, or SNR, measures the power of the desired information-bearing signal against the power of background noise. This noise floor includes thermal energy in the wires, atmospheric disturbances, and interference from other competing transmitters. This chart shows how connection quality scales with SNR in decibels. If the ratio drops below 0, the noise floor dominates, becoming unreadable static. Push it above 30 decibels, and the signal stands out clearly, allowing maximum data transmission rates. Because engineers cannot infinitely increase transmission power without causing global interference, and bandwidth is physically capped, the entire evolution of telecommunications has been a search for mathematical workarounds to maximize the data we can push through this strict limit. To escape the limitations of rigid analog circuitry, engineers had to translate continuous physical waves into discrete mathematics. This translation happens through the analog-to-digital conversion, or ADC, pipeline. The ADC is a multi-stage process that measures physical waves and outputs binary code. The first stage is sampling, where the continuous wave is converted into discrete measurements taken at regular intervals. According to the Nyquist-Shannon sampling theorem, the system must take samples at a rate at least twice the maximum frequency of the signal to reconstruct it accurately. If that sampling rate is too low, the system suffers from aliasing. Aliasing is a distortion phenomenon where high-frequency waves are mathematically folded into the lower-frequency spectrum, permanently corrupting the data. Once sampled, the signal enters quantization, where its continuous amplitude is snapped to a finite set of discrete levels. Through encoding, each of those specific levels is assigned a unique base 2 binary code. Now that the physical wave is represented as math, digital signal processing, or DSP, takes over. DSP relies on programmable algorithms to apply mathematical filters, like bandpass or notch filters, which calculate and strip away unwanted noise from the desired signal data. By moving into the discrete time domain, networks replace vulnerable physical waveforms with programmable logic, setting the stage for advanced data manipulation. With the signal digitized, the goal shifts to maximizing spectral efficiency. Spectral efficiency measures the rate at which data can be transmitted within an assigned bandwidth. To increase it, transmitters use digital modulation. This visualization maps the states of different digital modulation schemes. Basic schemes like binary phase shift keying shift a wave's phase between two states to represent a 0 or a 1. By manipulating both amplitude and phase simultaneously, engineers created quadrature amplitude modulation, or QAM, grouping multiple bits into a grid of possible symbol states. As data demands scale, moving to 256 QAM transmits 8 distinct bits per symbol, drastically increasing density. But tightly packed symbol states require an immaculate signal-to-noise ratio. Moderate background noise causes overlapping coordinate points, misreading the bits. To protect against frequency-selective interference and multipath fading, where signals bounce off buildings arriving at different times, networks utilize orthogonal frequency division multiplexing, or OFDM. OFDM is a modulation technique that splits a high-speed data stream into many lower-speed parallel subcarriers. Instead of sending one fast, fragile stream of data, OFDM divides the labor. Because these parallel subcarriers are mathematically orthogonal, they overlap tightly in the channel without interfering with one another. While advanced modulation and OFDM achieve massive capacity, They make the physical signal incredibly fragile, necessitating a mathematical safety net. Mobile environments guarantee that physical interference and burst errors will occur. If a base station had to halt and request a retransmission every time a bit flipped due to environmental noise, the network would stall immediately. The solution is forward error correction, or FEC. FEC is a digital signal processing function that mathematically detects and repairs errors at the receiver end, artificially boosting the effective SNR, a benefit known as coding gain. Before transmission, the system attaches redundant parity blocks to the message. If the signal sustains damage in transit, the receiver's algorithm uses these extra blocks to mathematically deduce the original sequence and rebuild the missing ones and zeros. Early systems relied on legacy block codes, like Reed-Solomon, which were highly effective at fixing localized burst errors. Modern cellular data requires continuous codes that evaluate a constant stream of bits while maintaining memory of previous states. Advanced iterative algorithms, specifically low-density parity check and polar codes, are the mathematical engines driving 5G data channels. These codes allow networks to operate remarkably close to the theoretical limits defined by the Shannon capacity. Code logic is now just as essential as hardware transmission. Without error correction algorithms running in the background, high-speed wireless broadband would instantly collapse under its own error rate. Despite advanced digital processing and continuous mathematical repair, the electromagnetic spectrum remains a finite physical resource that is rapidly running out of available space. Historically, government bodies like the Federal Communications Commission and the National Telecommunications and Information Administration managed this resource through static, exclusive allocations. This created a rigid system. Licensed spectrum guaranteed interference protection for carriers, but left bandwidth sitting idle in specific areas. Unlicensed spectrum, like Wi-Fi, fostered open access and lower costs, but offered zero protection from congestion. This chart maps the Citizens Broadband Radio Service. Regulators introduced CBRS for dynamic spectrum sharing, splitting users into 3 tiers: incumbents, priority access, and general authorized. A spectrum access system controls access in real time, instantly reassigning channels so spectrum never sits empty. The system strictly enforces priority. General users must yield to priority licensees, and all commercial traffic must immediately vacate the channel the second a Tier 1 incumbent, like a U.S. Navy radar installation, requires the frequency. Automated regulatory logic now serves as an active component of the network architecture, enforcing spectrum access in real time. Current 5G infrastructure maximizes spatial efficiency using massive multiple input, multiple output, or massive MIMO. Massive MIMO uses arrays of dozens or hundreds of antennas to focus individual beams of radio energy directly at specific devices, increasing capacity and reducing local interference. These high-capacity wireless edges are entirely dependent on an immense backbone of optical fiber. These lines rely on dense wavelength division multiplexing. DWDM is an optical technology that uses different colors of light to carry multiple distinct data streams through a single physical fiber, routing the actual global traffic. As research moves towards 6G, the architecture is shifting toward AI-native, distributed computing platforms. This schematic illustrates how machine learning models are replacing traditional, rigid digital signal processing math. Tasks like channel estimation, predicting exactly how a signal will reflect off the physical environment, are now handled by neural networks that adapt to changing conditions in real time. To handle extreme interference, networks are deploying generative adversarial networks, or GANs. A GAN is a class of machine learning frameworks where 2 neural networks can test with each other. By learning the actual data patterns rather than relying on predefined equations, they can extract a clean signal from noise that would overwhelm a standard mathematical filter. This intelligence enables integrated sensing and communication. ISAC is a capability that uses radio transceivers to perform high-resolution sensing. By analyzing how radio waves bounce off physical objects, 6G turns the global grid of communication nodes into a continuous sensor array, capable of tracking drones or monitoring healthcare metrics while simultaneously transmitting data. From a single analog wave fighting thermal noise to an AI-driven, dynamically governed global nervous system, the history of connectivity is the continuous triumph of code over the physical limits of nature.